残酷な天使のように少年よ神話になれ青い風が今胸のドアを叩いても私だけをただ見つめて微笑んでるあなたそっとくれるもの求めることに夢中で運命さえまだ知らない痛いけな瞳だけどいつか気づくでしょうその背中には遥か未来目指すための羽があること残酷な天使の手で窓辺からやがて飛び立つほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話になれ。
Yeah, Bill, I'm gonna need those on my desk by 2. What? What? Those numbers are unbelievable! Well, then buy it! Sell it! Oh, hello! Let's get started. Okay, everyone, we're back with section 4.5, optimization problems. This is a cool section. This is a good section because you can actually use this. You can use this all of the time. Now, granted, most people don't have a lot of reason to optimize, plenty of normal things that just come up in their everyday lives, but the cool part is that you can. When it actually matters, now you'll have the skill to do it. It's neat. We'll get a lot of good examples in here. So, section 4.5, optimization problems. The theme of this section, as you might guess from the title, is optimization. This is a topic that arises in virtually any discipline that relies on mathematics in some form or another. So, pretty much all of them. So, a structural engineer might ask for the dimensions of a beam that maximizes the strength of a structure at a specified cost. A packaging designer might seek the dimensions of a container that maximize the volume of the container for a given surface area. Airline strategists need to find the best allocation of airliners amongst several hubs to minimize fuel costs and maximize passenger miles. In all of these examples, there's one thing in common. The challenge is to find an efficient way to carry out a task where efficient could mean least expensive, most profitable, least time consuming, or whatever else you want. There are many other ways you can measure this. So when you're dealing with an optimization problem, the general flavor of it is that we want to, as you could guess, optimize a given quantity in some sense under certain conditions imposed on the possible solutions. So these conditions imposed on our solutions from the very beginning, from the outset, are called, as you might expect, constraints. They're the things that constrain the possible solutions we could have. Now, the quantity that we wish to maximize or minimize in other cases, we'll call this the objective function. So at their heart, optimization problems take on the following form. What is the maximum or minimum value of an objective function subject to a constraint provided to you? All right, let's get into it. Okay, guys, so first up, we'll need some sort of general guidelines, principles for dealing with optimization problems. Let's try to break it down into a list of 6 items that will let us handle any of the optimization problems that get thrown at you in this class or in any regular calculus class. So, step number 1. We're going to read the problem carefully, like you always should. This should always be the first step of any problem. Then we're going to identify the variables, organize the given information in a picture. I.e., label, and sketch. So step number 1, sketch and label, or label and sketch. There we go. Get the general sense of what's going on. Step number 2, we're going to identify the objective function, the function we're going to optimize. We're going to write it in terms of the variables of the problem. I.e., step number 2, formalize it. Step number 3, identify the constraints. We're also going to write them in terms of the variables in the problem. Really, you can combine this with step number 2 if you want. Same thing. Both of them, we're just formalizing it. Okay. Step number 4, we're going to use the constraints to eliminate all but one independent variable in the objective function. So this part isn't as clear to see how it'll work until we'll actually do an example. But this step you can think of, if you want, as a simplify. Take into account the constraint to simplify the thing you're trying to optimize. Cool. Step number 5. With the objective function expressed in terms of a single variable, we're going to find the interval of interest for that variable. So this step is basically just figure out what values make sense. Terrible K. There we go. Step number 6. Use the methods of calculus to find the absolute maximum or minimum value of the objective function on the interval of interest. If necessary, this might also mean that we have to check the endpoints. I'm going to stress that because that is one step a lot of people forget. Okay, we got all these different rules here. We got this long program for us to deal with optimization problems. This is way less helpful than actually just doing one. So let's do an example. Okay, everyone, on to the first example. Example 13. Here we've got a rancher that's got 400 feet of fence for constructing a rectangular corral. One side of the corral will be formed by a barn and requires no fence. 3 exterior fences and 2 interior fences partition the corral into 3 rectangular regions. What are the dimensions of the corral that maximize the enclosed area? What is the area of that corral? So before we just get into it, let's just stop to really think about this. Should we expect that there is an amount that maximizes the area? Yeah, I think it's actually pretty fair. So the idea is that if we're constructing lengths of fence, then just even for the example where we're working with a straight up square, with a side of length X and a side of length Y, we should still expect to be able to maximize the area. So for example, if I chose X to be 0 and just put all the fence right next to each other in one very two very close to each other lines, I wouldn't enclose any area whatsoever, would I? Similarly, I could do the opposite with X. So it seems like on one hand, I'll get 0 area when X is 0, and I'll get 0 area when Y is 0. And if I choose anything slightly bigger than 0 for one of them, then I'll have to, it'll get a little bit bigger, and then it's got to come back down. I mean, this is not really the shape of what we're graphing at all. What we're really graphing here is something that has 2 variables as an input and 1 number as an output. So you put in 2 numbers, you get out 1 number. You put in an X, you put in a Y, you get out an area. So if we wanted to actually graph it, we'd have to graph it as like a 3D graph, if you've ever seen those. I.e., we'd be putting in something on an x-axis, something on a y-axis, and we'd be getting out something on a z-axis. So I'd take some value of x and some value of y, and that would go on up to some value of z. See what I'm saying? Something like this. So it's going to be hard to visualize a lot of these functions before we go in and make things a little bit easier. But intuitively speaking, we should probably suspect that there is some sort of a maximum, just because we can get zero area by putting either variable equal to 0, and we want to choose something in between those two zeros. So let me get there we go, back to a good size. All right, so let's start out with our first step. The first step is just to do a little sketch and label everything. So what I've done here is I've saved us the time of watching me try to painfully draw a sketch here, and instead we've just got ourselves our barn. This big box right here, yeah? And what we're doing is we're building a rectangular corral that encloses 3 rectangular regions. So these 3 rectangles. So one side of the corral is formed by the barn. We don't need anything there. And then we got these 1, 2, 3, 4 vertical fences, and then 1 horizontal one, at least in how I've drawn the picture here. So since all of these ones running perpendicular to the side of the barn there will have the same length, let's just label that as X. Okay, and then we'll pick the other side, let's just call it Y. Good names for variables, why not? Okay, now let's start to think about what's going on with these variables. What can they take values in? So for one, if these are going to be lengths, then we at least need them to be greater than or equal to 0. So that is a fair enough assumption. X is going to be greater than or equal to 0, and Y is going to be greater than or equal to 0 as well. So the total amount of fence is going to be 4x plus y. So this is the total amount of fence, 4x plus y, because I've got 4 sections of length x, 1 section of length y. So our constraint is going to be, well, the amount of fence we have, which is going to be, as we can see from the problem, 400 feet of fence. So that's 400 feet. So we know that 400 equals 4x plus y. And if that feet there is going to confuse anybody, I'll just erase it. But, you know, there are units implicitly in everything here. We'll just leave it a little bit cleaner and not always write them down. So here, let me even get rid of this fence bit right there and just write down our constraint equation. So our constraint is 400 equals 4x plus y. All right, so I should have chosen a bigger sized eraser there. All right, there we go. 400 equals 4x plus y. Now, the next thing we're going to do is we're going to talk about the objective function. So this is our constraint. Now we're going to want to find out what the objective function is. Okay, so we got our constraint. And the thing we're trying to maximize or minimize, in this case, certainly maximizing, is going to be the area. So I'm going to write this as a function of 2 variables just for the moment. The same way we'll write f of x, I'm going to write a of xy equals x times y. Because this is length x, this is length y. So the area right here, in terms of x and y, this is exactly what the notation of ax comma y is telling us, that area depends on x and y. The area is just given by x times y. It's the area of a rectangle. Easy enough. So that's our objective function. All right. Our objective function is axy equals x times y. So the thing we're going to want to do now that we've got our objective function, now that we've got our constraint, is that we're going to want to solve our constraint for one of the variables and then plug it in to our objective function So our objective function stops being a function of two variables and starts being a function of one. Okay, now you don't have to write this in function notation, the way I've written AXY right here. Maybe if that confuses you, don't write it like that. In general, I won't write it like this. This is just to highlight exactly what's going on right now. So as you can see down here, I'm just writing it as A equals X times Y. So taking our constraint equation, 400 equals 4x plus y, we can solve that for y. That is, we get y equals 400 minus 4x. I'm just moving that 4x to the other side of the equation. I'm not going to write that step down. You guys can see it. Okay, so now since I know that if I'm obeying this constraint, then y has to satisfy 400 minus 4x equals y, then I can turn my area function, expressed in terms of x and y, into a function of only one variable, x. That is, looking at what's going on right here, we're just going to take this thing for y and we're going to plug it on in. We're just going to take 400 minus 4x and we're going to plug it in for y. So we get x times 400 minus 4x as our area function. This naturally gives us 400x minus 4x squared, and this is just a function of one variable. And at this point, all we're going to do is the stuff from the last couple of sections. We're just going to find a global max on a closed interval. Okay, so since x has to be between 0 and 100 because there are 4 sections of fence, we're just going to maximize the function 400x minus 4x squared on the interval from 0 to 100, the closed interval from 0 to 100. So one way to view what's really going on here is that I've got this function a of xy is equal to x times y. And what I'm doing is I'm plugging in 400 minus 4x in for y, just like this. And then I just go through and I do a little bit of algebra, and I get 400x minus 4x squared. Exact same thing as what you get over here. So this is why I opted initially to show this function notation right here, because all we're doing is composition. The maybe kind of confusing part at first, if you don't directly see it, is that we're only doing a composition in one variable, if you want to think of it like that. That is, we're replacing y with a function of x. See what I'm saying? Okay, and now we just have a function of x. So from here on out, let's just write this as a of x instead of a of xy. This is a different function now. This is a function of one variable. The a up here, this guy, that's a function of two variables. Okay, so this a down here, like we said, we're maximizing a of x is 400x minus 4x squared on the interval between 0 and 100. Since we only have 400 feet of fence available and we're looking at a picture like this, yeah? So if I put 100 on each of these x's, I've used up all my fence. Okay, so I can't use any more than that, otherwise I'd use up all my fence. I certainly can't use negative amounts of fence. That's weird. That wouldn't make any sense. So we just take this function and we optimize it on this interval. First thing to do, take a derivative. We'll get 400 minus 8x. We're going to set it equal to 0, and we're going to solve. This is just finding critical points. Since our function is a polynomial, all of the critical points will be places where the derivative is equal to 0. So 400 minus 8x, we can solve that. That has a solution of x equals 50, which if you want to see, just comes from 400 minus 8x equals 0. That is the same as having 400 equal to 8x, and that's the same as having x equal to 400 over 8, which is 50. So x equals 50 is our critical point. So all we got to do now, since we've got a closed interval and a continuous function, is we have to test the critical point and the endpoints. So, and this is easy right here because we know that a of 0 and a of 100 are both 0. They either have only fence along the y part there, so these guys would be length 0, or all of these guys here are length 100, and there is no room left for that y. Okay, so both those guys are going to give 0. Can you guess what's going to happen? Yep, a of 50 gives an area of 10,000 feet squared. That's the absolute maximum value of the area, and it occurs when x is 50. So, another way you can see that this is immediately going to happen is just by looking back at what a of x is, what the area function is after we put in our constraint. 400x minus 4x squared, that's a parabola that opens downwards. The maximum occurs at the vertex. It's pretty straightforward to see. If you just draw a little picture, that's the highest point on a parabola opening downward. Easy enough. So, using the constraint, we evaluated our objective function of 2 variables and turned it into a function of 1 variable. Then, using the techniques we've learned so far, we just found the maximum on our interval that, where stuff even made sense. So the optimal length of the corral is 200 feet, and the optimal width is 50 feet. So the maximum area of 10,000 feet squared is achieved with dimensions of x equals 50 feet and y equals 200 feet. Just redrawing our little picture quick. We've got 1, 2, 3, 4 things of length x. All of those guys are 50 feet. And then this bottom part is 200 feet. Cool. That's kind of neat. If we hadn't gone through and just directly calculated this, I think that, if you're just building it on the fly, you probably wouldn't have ended up with this and got the optimal area. If you were just guessing, would you have chosen it? It's useful. And there's one thing to notice here. So we had 4x. This is the length of these vertical sections in total. And then we have y as that part. Notice 4x equals y in this case. That is 4 times 50 equals 200. So this is a general theme. And in fact, we'll see this in a whole lot of different ones. When we're maximizing an area, just for, say, a box or something, maybe if both sides are length x, then it's maximized when these two x's have the same, sorry, I should be a little bit more clear right there because that one's not a fun one to maximize. Here, let me be slightly more precise. I got ahead of myself there. So, if you're maximizing just a rectangle with an x and a y, this area is maximized when x and y are equal to each other. Put those guys equal to each other, you maximize the area. When you start splitting it up, then you can maximize the area of stuff like this. If you got x, 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 and then like a y or something like that, right? You can maximize this guy by setting, the sum of these equal to that. So we'll see this very specifically. Maybe we'll even go through and actually prove it in the general case in a minute. But for now, this is just good intuition. Good intuition for what's going on. Basically, expect that when you're maximizing a quantity like area, there should be some sort of intuitive notion of balance going on. That is, somehow, one side and the other side have to sort of be not necessarily directly equal, but at least proportional in some very nice way. Cool. Another example. Okay, we're back with another example. Example 14. So, suppose an airline policy states that all baggage must be box-shaped with a sum of length, width, and height not exceeding 64 inches. what are the dimensions and volume of a square-based box with the greatest volume under these conditions? So the basic gist of it, if you've ever flown on a plane before, you've probably encountered something like this. There's all these arcane luggage policies that you have to take into account when you're trying to fly on a plane, and they are frequently a little bit annoying to get right. It is super frustrating to have to spend a bunch of extra money to take your bag with you on a trip just because it is a couple of inches too big in some dimension or something like that, right? You've seen those little things they make, the little boxes they make you put your bag in to see if it qualifies for the airline, all that stuff. Okay, so here's the gist. Let's start out by making a little picture. All right, so we've got a square-based box. We've got three things here: length, width, and height. Our constraint is that length plus, or here, let me use the same lowercase l, plus width plus height should not exceed 64 inches. So really it's less than or equal to 64 inches. But if you guys are fine with this, if you guys will accept this little bit of reasoning here without too much justification, would you believe that using less than 64 inches certainly won't maximize our volume? I think that one's relatively clear. So really what we can do is we can just look at the constraint of length plus width plus height equals 64 inches. And like before, the units are there. They're just implicit. We're going to erase them and let everything be a little bit cleaner here. Okay, so since we're dealing with a square-based box, the length is equal to the width, since the base of the box is square. Okay, so really, this constraint becomes 2w plus h equals 64. Now, what are we trying to maximize? This right here is our constraint. Well, it would be the volume of the box, yeah? V equals L times W times H, length times width times height. Or in our case, volume will be, since L and W are equal, it'll be W squared H. Cool. All right. Let's really get into it and start very much going through the situation directly. Now that we've got the basics down, now that we've sketched a picture, let's try it out. So, we're looking at a square-based box whose length and width are W, the same. The length and width are the exact same. The height is H. By the airline's policy, our constraint is that 2W plus H is equal to 64. The objective function is the volume function, which we just found. This is W squared H. Now, we have to somehow figure out how to eliminate either W or H from our objective function right there. We want it to just be a function of one variable because we know how to deal with those. At least so far we do. It is possible to deal with functions that have more than one variable, and if you take more calculus classes, you'll definitely learn that. But for now, we want to get it down to one variable. So, taking the equation 2w plus h equals 64, our constraint, we're going to solve for one of the variables and plug that into our objective function. Okay, so how about let's solve for h, because that's really easy. So just subtract 2w from both sides in the constraint, and we end up with h equals 64 minus 2w. So, plugging this in for h, we'll get that the volume is equal to w squared h, which is w squared times 64 minus 2w. And just multiplying that w squared on through, we'll get 64w squared minus 2w cubed. So now we've expressed the objective function in terms of a single variable, just in terms of w. Notice that W has to be non-negative, and it can't exceed 32. Why is this? Let's pause. Let's make sure we understand. So, since we can't have any negative widths, W at least has to be bigger than or equal to 0. And since 2W plus H equals 64, and H also can't be negative, the smallest H can be is 0. Put in H as 0, and that tells you that W equals 32. So that's the biggest that W can be. So the domain of our volume function that we found in terms of W, this guy right here, 64W squared minus 2W cubed, is going to be the closed interval from 0 to 32. 0, 32 with brackets, or if you like it in inequalities, 0 less than or equal to W less than or equal to 32. Now we'll find the critical points. We're just back in the same old stuff as before. We're through all the new stuff. We set up our picture. We drew a picture. We got our constraint. We figured out what's going on in our problem. And then we finished it off taking our constraint, solving for a variable, plugging it on into the objective function. So now all we got to do is find critical points, test at the critical points, and test at the endpoints. We don't have to really worry about critical points defined by situations where, the derivative would be undefined, because our function is a polynomial. Its derivative exists everywhere. So, taking a derivative, we'll get v prime of w is 128w minus 6w squared. Just go through it with the power rule, take in that, nice, easy polynomial right there with the power rule. That's a pretty straightforward derivative. So notice that both terms have a w. Both 128 and 6 are even, so let's factor out a 2w. We'll end up with 2w times 64 minus 3w, that whole quantity. And when we're finding the critical points, we'll set it equal to 0. So just looking at that, one of the zeros will be when w is 0, and the other one will be when 64 minus 3w is equal to 0. So 64 minus 3w equals 0. This tells us that 64 is equal to 3w, or that w is equal to 64 over 3. Bam! We got our two roots. W is 0 and w is 64 over 3. Now we can use either the first or the second derivative test. It depends whichever you find easiest. So if we use, let's say, the first derivative test, we could check signs and see when this guy right here, v prime of w, changes from positive to negative or negative to positive. I think in this case, the second derivative is actually a little bit easier. So if we use the second derivative test, notice, and I'm going to write this right off over here, v double prime of w, just using this part right there, will be 128 minus 12w. Okay, cool. Plug in 0, what do you get? You get 128. So v double prime of 0 is greater than 0. What about v double prime of 64 over 3? So notice that 12 is 3 times 4, so 128 minus 4 times 64, this will be negative 128. So that's less than 0. Bam. All right, fair enough. So at one of them, I've got a second derivative that's greater than 0. One of them, it's less than 0. When the second derivative is greater than 0, that's a situation where it looks like a cup facing up. When the second derivative is less than 0, that's a situation where the function's graph looks like a cup facing down. If you've got a point at the top or the bottom, these correspond respectively to minima and to maxima. Okay, cool. So using either the first or the second derivative test, we can pretty easily see that w equals 64 over 3 corresponds to a local maximum. It's because we're looking at this situation based off of our application of a second derivative right there. We just evaluated the second derivative of that critical point, saw that it was negative, telling us that our function was concave down there. And that tells us that We're sitting on the top of that little hill. So the volume function has an absolute maximum of 64 or of 9,709 inches cubed approximately since, oh boy, sorry. The volume function has an absolute maximum of 900 or 9,709 inches cubed since evaluating at the endpoints, just like in the last example, gives us 0. So this is the absolute maximum volume you can enclose in a suitcase that conforms to the airline's regulations. And the dimensions of the optimal box are 64 over 3 inches for W, and solving for H, 64 over 3 inches again. So notice that. H is equal to 64 minus 2W. We found that all the way up here. So when we get our final answer for W, if we want to find H, we just have to plug it right back into this. This is our recipe to find H after we know a W. So plugging that on in, 64 minus 2 times 64 over 3. And if you want, you can write 64 as 3 64 over 3s minus 2 64 over 3s. And that's just that's just 64 over 3. That's just one of them. Take 3 of them, get rid of 2 of them, you only got 1 of them left. And hey, wouldn't you know it, our optimal box, this is exactly what I was saying last time. Our optimal box, oh my lord, does it have a nice bit of symmetry going on here. Here's what we're looking at. We got 64 over 3 inches, 64 over 3 inches, and a height of 64 over 3 inches. They're all the same. The thing that maximizes volume, a perfect cube. Cool. There's definitely some nice symmetry and proportionality going on here. Neat. Let's do another one. Okay, we're back. On to another example problem. Example 15. An 8-foot tall fence runs parallel to the side of a house 3 feet away. What is the length of the shortest ladder that clears the fence and reaches the house? We're going to assume that the vertical wall of the house and the horizontal ground have infinite extent. That is, we're just going to assume that they are as long as we need them to be for this problem to make some sense. So let's start out by sketching ourselves a quick picture. So I'm going to take the ground here. I'm going to make the side of the house up like this. So that's the good old-fashioned house, and here I got myself a little fence. And none of this stuff necessarily has to be to scale. We're just doing this for convenience. So here, let me label a little bit better. Let me call this the house over here. So here's the house. This bad boy is the house over here. Okay, so we got ourselves a house. We got ourselves a little fence right there. All right, let's sketch what's really going on in this picture. So the idea is that I've got a fence some distance away from a house, and I am trying to find a ladder that can clear it. So as I just drew, it is certainly possible to clear the fence with a ladder. You can pretty easily see this, you could just put the base far enough away and have it be tall enough. All right. Similarly, I could go at a pretty dang, steep angle like this, or if I really wanted to, this would take us way the heck off the page there, So it is totally possible to do this. But somewhere between these extremely steep and incredibly long ladders and these ones that are very long and far away at a shallower angle, there is some ladder length that is minimizing how much ladder you need to get across the fence and up there. So let's clear this up a little tiny bit and just make everything pretty smooth. So basically, the idea of it is that if I draw a little ladder in, all right, I'll do it like this, and I'm going to start labeling a few things. So the fence, now I haven't drawn this to scale to be clear. This is 3 feet distance right here. That's how far away the fence is from the house, about 3 feet. Okay, fair enough. About 3 feet away from the house, that little fence. Okay, good stuff. So, 3 feet there. The fence is 8 feet tall. So this bad boy here is 8 feet tall. And I'm going to label this down here. Let's just call this, I don't know, how about X? It seems like a fair variable, yeah? And let's call the length of the ladder something like L. So ladder's length is L. X is the distance of the ladder from the ladder to the fence. And then let's call this distance over here, i.e. how far up on the house the ladder is hitting. Let's call that, I don't know, B. Why not? We'll call it B. So notice, just using the Pythagorean theorem, I already have a relationship between all of these guys. So I know that L squared is equal to, well, I got this side right here. So let me throw another color here to make everything a little bit clearer. I got this side right there. I got this whole base down here. And then I have the length of my ladder as the hypotenuse for a triangle. So using this, I can see that I have L squared is equal to B squared plus the quantity x plus 3 squared. There we go. So we've got a relationship between all of these variables. Let's start digging into how we're actually going to solve this problem. So, on we go. So we expect a minimum ladder length, just like we drew there, because you could put the foot of the ladder far from the fence and have it clear the fence at a shallow angle, but then the ladder would be quite long. Conversely, you could put the foot of the ladder very close to the fence, so it clears the fence at a very steep angle, but once again the ladder ends up long. So the length function finds its lowest value somewhere between these two things, somewhere between these two extremes. Okay, so the objective function in this problem is the ladder length L. Let's have x specify the distance between the foot of the ladder and the fence, and then we'll express L as a function of x. Okay, the Pythagorean theorem, just like we looked at before, gives us that L squared is equal to x plus 3, that whole quantity squared, plus b squared, where b is the height of the top of the ladder above the ground, where it hits on the side of the house. Now, the big important thing here is similar triangles. So this part is where we really need to be careful. So, looking back at our picture, you can see that there's really two triangles here. I'll grab another color to explicitly highlight this. That is, there's this big green triangle, and if I use the fence as a side of a triangle, I have another little triangle right down in here, that orange one. You see what I'm saying? I got this little orange triangle right here. Yeah? Okay. So this might be a little bit unfamiliar at first, but just remember that similar triangles, basically the gist of it is that they have the same ratios between the lengths of their legs. This makes sense. You scale a triangle up, then the ratio of, one leg to the other should still be the same if I've just scaled it up. Doesn't matter at all. Okay, so 8 over x should be the same as b over x plus 3. See what I'm saying? B here over x plus 3 down here should be the same as 8 over x. All right, now I can solve for one of these variables substitute it into my objective function, and get something in terms of one variable. All right, let's see how this works. So, just using that, we've got 8 over x equals b over 3 plus x. Notice, I think here I wrote it the other way around. It's definitely the same either way. You can do it x over 8 equals x plus 3 over b. Doesn't make any difference. Same stuff. Always going to work out just fine. But whatever way you find most convenient, you can definitely do this. So, 8 over x equals b over 3 plus x. Now we'll use this and we'll solve this constraint for b. Then we'll substitute this expression into the length squared in terms of x. So, just noticing now that if I want to get b by itself, what I'll end up with from 8 over x equals b over 3 plus x, what I'll end up with is that, and now all I have to do is multiply by 3 plus x to get that on the other side and get b by itself. What I'll get is that b is equal to 8 times the quantity 3 plus x over x. And that's exactly what you're seeing right here. I'm just substituting that in for b, just right up there. Same thing. All right, and now that I've got this, notice when I square 8 times the quantity x plus 3 over x, what I'll end up with, if I square everything, is I'll get 8 squared times x plus 3 squared over x squared. Let me make that 2 a little bit better. And so, 8 squared is 64. Now both of these terms have an x plus 3 squared in them. So I'm just going to pull that x plus 3 squared out of both of them and end up with a 1 plus 8 squared, 64, over x squared. All right, now what we can do is we can go through and we can solve for L and find critical points. But this is a really good trick. We're going to make our lives a little bit easier by noticing that length, it's non-negative at least, right? Length is always bigger than 0, or at worst it's equal to 0. Okay, so if you take something non-negative and you square it, what happens? Well, the nice part is that you'll end up with local extrema at the same points. So L and L squared have local extrema at the same points because L is a non-negative function. Basically, squaring's not causing anything to turn positive. Squaring is a strictly increasing function to the right of 0. You know, x squared, it looks like a parabola opening upwards, right? All it does is make things increase. So if you've got a maximum for L, you got a maximum for L squared. If you got a maximum for L squared, you got a maximum for L. You got a minimum for L squared, you've got a minimum for L, and vice versa, you know, on and on. So they have the same local extrema at the same points. So let's just stick with the function L squared. Let's just name our function L squared. Don't even think of the 2 as really even being there. L squared is just its name. All right, so the function named L squared, if I take its derivative, and be careful here, we're not really doing any fancy chain rule or anything, we're just naming our function L squared. We're not really like treating it like a function that's being squared, we're just naming it L squared. Okay, so dl squared dx, that's just ddx of the function we found up here, what we'd write L squared as, this bad boy. Okay, so we're just going to ddx that guy. Looks like a little bit of product rule and maybe a little bit of power rule. So let's run through it really quick just to make sure we got it down. So we're taking the derivative of, let me just write this real quick, ddx of the quantity x plus 3 squared times the quantity 1 plus 64 over x squared. Okay, now that I got that down, I can move on over. Perfect. There we go. So we got this guy, we're going to derive it out. All right, so product rule, first thing we're going to do, I'll just write it out step by step. We'll get ddx of the first part, which is x plus 3, that whole quantity squared, times the second part, 1 plus 64 over x squared, and then we'll add on x plus 3, that little quantity squared, times the derivative of the second part, which is, just once again, and I don't even have to put any parentheses in there, 64 over x squared. Perfect. So, a little bit messy, but there we go. Let's just run through and derive it. So when I take the derivative of x plus 3, that quantity squared, I'm just going to use the chain rule. So I get 2 times the quantity x plus 3 times the derivative of x plus 3, but that's just 1. So I'll leave it like this. All right, 1 plus 64 over x squared, that's just hanging around. And then I'll add on that x plus 3 quantity squared times the derivative of 1 plus 64 over x squared. So here it might be a little bit helpful to remember that 64 over x squared can be written as 64 times x to the minus 2. So we end up with minus 2 times 64 x to the minus 3, just using the power rule. All right, and we've got this derivative done. Really all we need to do now is just go through and simplify. So I'm going to take an x plus 3, and I'm even also going to take a 2 out of both terms, since I got a 2 and an x plus 3 in all of them. Okay, so now 2 times x plus 3, that whole quantity, times 1 plus 64 over x squared, plus x plus 3, I've still got one of those left over, times minus 64 x to the minus 3. So if you find it a little bit easier, we can rewrite this in a slightly different way. 2 times x plus 3 times 1 plus 64 over x squared. And then here I'm just going to write this as minus 64 over x to the third. And let me even make that slightly cleaner. Times the quantity x plus 3. So I'm just writing this chunk right here on the other side. Okay, now I can go through and simplify this. This isn't too bad. What will we end up getting? I'll just leave that 2 times x plus 3 out here. That's all good. In here, 1 plus 64 over x squared minus 64 over x to the third times x is just minus 64 over x squared. That seems fair. Okay, and then we'll get minus 3 times 64 over x to the third. Bam. So we can go on through and we can find a common denominator and simplify this down. And if you want to, we can do that real quick. But notice these two guys are going to kill each other right there. And so we get 2 times x plus 3. And then now that we got those two out of the way, we'll get x to the third minus 3 times 64 all over x to the third. Bam. So something like this, you'll end up here. But let's go back and let's really see what's going on. So as you notice, we're getting the same thing. I just put it all over that x to the third denominator. Easy enough. So since we know that x has to be greater than 0, since if you put the base of the ladder 0 feet away from the fence, then that ladder is just pointing directly upwards. We can tell that x plus 3 is not going to be equal to 0, since you certainly, it defeats the entire purpose of the problem. If we're trying to clear the fence, then we certainly can't take x to be negative. That would be putting it on the wrong side of the fence. So the condition that dl squared dx is 0, i.e. when we're finding the critical points, just requires that this guy is 0. Since we only have two options to make dl squared dx equal to 0, and one of them is out, this one is all there is. We need the numerator to be 0 if a rational function is going to be 0, so this guy's got to be 0, that x cubed minus 192. So going through and solving, x cubed minus 192 equals 0 tells us that x is equal to, what, the cube root of 192? And I believe that's precisely 4 times the third root of 3, something in the vicinity of 5.77. If you want to use the first derivative test, you can find that this critical point corresponds to a local minimum. All right, cool. Now, the thing to pay attention to here is that we could also use the second derivative test if you wanted to, but, and this is a great way to illustrate why the second derivative test is not always that clean, does anyone want to derive this whole nightmare again? Absolutely not. First derivative test seems way better. So if we're doing it, just pick something a little bit smaller than 5.77, and then pick something a bit bigger. So you could pick 5 and you could pick 6. Running on through and just punching it in a calculator, plugging it in here, you'll see that you get negative and then positive. Negative for something a little bit smaller than this bad boy, positives for something a little bit bigger. And that tells you that you're going down and then you stop and then you're going up. So it's at the bottom of a little valley. So it's going to be a minimum. And since this is the only minimum, the solitary local minimum, in the interval 0 to infinity, this is earnestly the absolute minimum. Fair enough. So the minimum ladder length occurs when the foot of the ladder is approximately 5.77 feet from the fence. So L squared of 5.77, something like 224.77 feet. So take the square root of that, and the minimum ladder length is approximately 15 feet. Nice, we did it. We brushed over a couple details at the end there, but I'm sure you can handle it. Cool. Calculus, yeah. Oh, a little proof, yeah. Calculus, oh, yeah. Oh yeah, a little calculus.
You big head on
Calculus, 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 calculus. Spend 10 minutes on a new problem. My bitch love do calculus. Ooh, I prove a theorem, I forgot its name. I can't buy bitch no math game. Rather go and buy textbooks. Calculus, calculus, calculus. Calculus, 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 calculus.